Today, I'd like to talk to you about automating other wheeled vehicles. Self-driving cars and trucks have been in the news really for the last decade, virtually. Ever since the success of the 2007 DARPA Urban Challenge, we've seen growth in interest, growth in experimentation, growth in investment in autonomous self-driving cars and trucks. Getting lost in all of this, however, is the reality that predating 2007, in fact, going all the way back to the 1950s, there has been successful automation of other categories of wheeled vehicles, both indoors and outdoors. In fact, in the 1950s, many factories had buried uh, induction wire uh, beneath their floor in paths that self-driving autonomous vehicles were intended to track. This worked extremely well, and it was very popular and remains so today. However, there are many other categories where research has been ongoing, where there has been marketing, where there has been interest on the part of the public, on the part of companies, and so on and so forth. And taking a look at these is something that I wanted to try to do, all with a view toward a suggestion of a possible paradigm shift. Not a new paradigm, but a paradigm, in fact, that's been borrowed from another category, a larger category to date, of automation. And I'm speaking of the kinds of robots that you frequently see in pictures of factories. Robots, let's say, that spot weld cars, where you may see an orange or a yellow robot, possibly a whole row of them, and passing in front of these units would be the frame of a car. Reaching out, uh, the robot quickly, precisely, impressively makes a spot weld. A spark flies out, and the frame proceeds on to the next station. One of the categories, besides the factory robots, is the whole idea of mowing a lawn. You know, mowing a lawn is something that is a bit tedious. You typically follow, for the most part, the same trajectory of the lawnmower from instance to instance, and it's something that really begs to be automated. Well, going as far back as the early 90s, there have been successful efforts to automate lawn mowing. Many of these, the ones that have survived, have been based on the idea of random motion, motion that is not designed to follow specific lanes, if you will, but rather that continues, perhaps roughly in a straight line, until a preset boundary is reached, at which time it moves off into another direction. Beyond that, there have been efforts to automate hospital delivery robots. This likewise is an effort that goes back to the days of Shaky, a famous robot back in the 60s, 70s, and 80s that was developed for multiple purposes, but that was able to use ultrasound, able to use various kinds of proximity sensing in particular, in order to find its way through the corridors of a hospital. In addition to these things, there have been efforts to automate floor maintenance. These have taken on different kinds of paradigms, different kinds of approaches. Some of them closer to that of Shaky, others of them closer to that of the random motion grass cutting robots. In addition to all of those things, there are still other possibilities. The one that I'm going to focus on today has been an ongoing effort on the part of several people to automate wheelchairs, to remove from the wheelchair user the burden of guidance, to remove, if not the burden of guidance, the need to have a human being, another human being, who's able to push this chair and pull it through a day-by-day trajectory that doesn't change, at least in many typical circumstances. What then is this paradigm that we might borrow from industry? Again, if you think back to these cases of the spot welding robots, these beautifully performing machines, what you see is actually a repetition of the internal joint rotation. So if you think of your elbow, for example, your elbow, it has a certain angle at the moment. And as you reach out for something, your elbow undergoes a transition of angles through several different values, a continuum of values, in fact, at the same time as other joints do the same thing. They synchronize, they coordinate, they work in concert in order to bring your arm through a sequence of, let's call them poses, and to a final destination where a workpiece, let's call it, is present and awaiting the operation of the tool or other object that you're bringing to it. Teach Repeat uses the teach pendant, a picture of which you see here, in order to bring about similar capability. And what the human does in this case is jogs, the J-O-G. It's the word that's used with this teach pendant in order to describe the careful positioning of all of the joints of the robot, frequently 6, in order to create a series of poses, a series of points, such that the robot will reach out and approach the target of interest from the right direction with the right orientation and in a sequence of positions that will guarantee the operation in question. What happens from there is that a computer remembers these joints, and there is a controller that controls the robot joints in order to come very close to passing through all of these joint rotations for all of the poses taught by the user. And what you see in the present video is the working out of that. It's very difficult to imagine how different this is from the way that we humans would do the same thing. If we were loading bags like this, we would be very dependent, copy after copy, on our eyes. This robot is blind. What it does is it repeats the sequence of joint rotations. It undergoes these copy after copy, and it does it in a way that, provided you keep all of the pertinent objects in the right three-dimensional position and orientation in space, works out to complete very successfully the maneuver of interest. This paradigm has been one that has been in operation really since the dawn of industrial robots, and it remains the norm to this day. I wanted to contrast that with the various paradigms that I mentioned previously for nonholonomic robots. By nonholonomic, I mean robots where there is still actuation of joint rotations or rotations, but where these rotations are not joints, but rather wheels, and where the relationship between the rotation of those wheels and the positioning of the load is not one that you can establish a priori in a kind of algebraic way. At most, this relationship, and at best, is differential. A differential form is one that does not support teach-repeat in the same way as the holonomic industrial robot. This cartoon shows you a bit of the distinction. In this cartoon, what you can see is an image of the wheelchair undergoing motion necessary in order to position itself and orient itself in front of the desk. Now you see that 2-degree of freedom wheelchair converting to a 3-degree of freedom Revolute robotic arm, a Scara type robot, one that operates in a plane, in this case a horizontal plane. Not only does it require 3 degrees of freedom, but it also supports teach-repeat. In other words, I can simply position each one of these 3 joints through the same sequence of movement and position and emerge with the same pose, the same position, the same orientation of the chair every single time. Not so with the robot that you see here. In this case, it's path dependent. Every time the chair strays from the nominal, let's call it taught sequence, there is a return to joint angles or to wheel rotations that will not guarantee as is guaranteed in the case of the holonomic robot, return of the chair to its taut terminal position. That's a problem. And it's that problem that we seek to remedy with the present technology. The technology is shown here in repeat mode. Steering comes from the ratio of the two rear wheel speeds. Wheelchair speed depends on control of wheel's average angular speed. The reference value or desired value of wheelchair speed is based on analysis of local data from the teaching event. Smaller taut path radius of curvature indicates a lower reference speed, as does close proximity detection of nearby objects. Detection in the current teaching event of new, closer still proximity further reduces the desired or reference speed. Steering control during this tracking event is based on the error in vehicle orientation relative to the taut path, together with error in lateral position. It is like steering a car in order to keep it centered on a white line in the road. Both the discrepancy in direction between car and line and the discrepancy in lateral position inform the ongoing steering process. But where is this white line? And how do the wheelchair's current direction and lateral position compare at any moment? These are the keys to extension of teach-repeat to non-holonomic robots. Two cameras, about a foot off the ground, look out from beneath the seat, parallel to the floor, in order to detect points pre-placed on stationary surfaces at the same elevation. Just as the two angles of spherical coordinates of stars have been precisely cataloged, so too the two components of in-plane position of the oval point cues shown here have been cataloged during setup. At any juncture along the taut path, a batch of recent camera detections of the small wall cues is considered. Just as an estimator of a tumbling satellite can apply camera-detected stars to correct and improve gyroscope-based integrals of satellite orientation, so too the batch of wheelchair cue detections can make very precise wheel odometry-based estimates and integrals of the in-plane wheelchair position and orientation. Very precise, but not necessarily very accurate. This precision-accuracy distinction is also important for teach-repeat of the stationary-based holonomic industrial robot. That robot's action is very precise in the sense of repeating taut poses, and such accuracy makes the global inaccuracy of the algebraic kinematic model unimportant. The same teach-repeat advantage can be had for the non-holonomic wheelchair. In particular, establishment of the virtual trace on the floor of the white line can be achieved by way of offline analysis of odometry and camera data from the teaching event. By careful analysis of observability and recency or locality of applied cue detections, estimates of the white line are generated together with a kind of local batch assembly weighting protocol to be applied to every subsequent tracking event. It is a version of moving horizons estimation that has also been applied to satellite attitude estimation. For the wheelchair, the resulting global accuracy is not good, but that does not matter because despite small modeling error, as seen here, repeatability is centimeter precise. This very high repeat precision can be very important for users in their own home. Managing transfer from the wheelchair to the bed can, in many cases, be achieved if and only if the terminal precision and orientation of the chair relative to the bed is very precise and the same every time. The teach process can be conducted without a rider and at arbitrarily slow speed. This permits careful and precise trajectory establishment, even when backing up, allowing termination that will be reliably close to an important stationary object, like the bed, such that upon arrival, the rider can transfer independently from the chair to that object. A question that goes unasked is why we would expect acceptance of autonomous high-momentum wheeled vehicles on public roads if, despite decades of development, automation of other low-momentum vehicles, often in private or semi-private settings, has yet to make itself conspicuously successful. The great real-world success of mechanical robots is the likewise decades-old, in fact much older, joint-level teach-repeat of industrial robots. For decades, forecasts of replacement of this original mode of control have been met with determined and successful effort and expenditure to make the paradigm work for more and more applications. Applying teach-repeat to non-holonomic robots largely eliminates the highest of the industrial costs, the need actively to preposition and fixture workpieces. Most wheeled applications only have the counterpart passive need to keep toilets, beds, furnishings, and so on stationary. The apparent restrictiveness of teach-repeat is less than imagined. In the bag stacking process, several different approaches to release onto the stack can be established or taught. Following the elaborate bag-filling sealing sequence, these can be automatically selected from based on criteria such as count or sensor-based stack elevation measurement. Motion can likewise be automatically halted or reversed. The same prospect for versatility awaits the non-holonomic robots. Multiple paths connecting portions of longer trajectories can easily be established and drawn upon automatically. Multiple previously taught movements connecting the same points leaves open many options for real-time algorithm construction, automatic or human-selected decision-making. One undisputed benefit of self-driving car research is the refinement of resolved proximity sensing. Even with such resolved sensing, obstacle avoidance for the wheelchair is difficult due to the need to get extremely close to objects. Policies conservative enough to be safe in general would not permit this. The precise repeat consistency, however, enables a solution. Select profiles of sensor readings can be established to be highly characteristic and repeatable as a function of distance to go. Small introduced impediments, such as the bathroom scale, impediments which might have been ignored in any policy that would permit such close approach, stick out like a sore thumb. When all is clear, the chair can advance.